Good morning, class. Welcome to class 9. Of course, electronic theory of solids. In today's class, I'll be demonstrating you the questions which are based on the magnetization. So there will be some problems, topic questions, and on which I'll be telling like how to approach those questions, where to start, and then how to calculate the magnetization and the related quantities. So having said that, let me start with the very first question, which goes like, you have question, consider the vapor to be an ideal gas. Now find the paramagnetic contribution to the molar Curie susceptibility of cobalt That's the atomic number which has been shown, which forms an atomic vapor at the temperature of T is equals to 1768 Kelvin, and for this one the hint is you need to calculate the Landesi factor of cobalt. item, and the land energy factor goes as G is equals to 3 by 2 plus spin part SS plus 1 minus orbital part LL plus 1 by 2J plus 1. This has been already derived in the class, so you can follow up for the more details. So this is 2J J plus 1. Yeah. So we know from the class notes that Curie susceptibility solution. So referring the class notes, Curie susceptibility is Na, Avogadro number, land energy factor G, mu p per magneton square by 3 J plus 1 by kBt. Let me label this equation as 1, and the value of the G is also given, which is 3 in the hint of the question, which is 3 by 2 SS plus 1 minus LL plus 1 by 2 J plus 1. So effectively we need to calculate the G. If we know the G in the system, we know the paramagnetic susceptibility, the Curie susceptibility basically. So the material is cobalt. Yeah, material is cobalt. So cobalt atomic number is Z is equals to 27 and 3d7. So if you start filling, 1 second, someone is there to join. Yeah, so if you start filling the band of this d orbital, so 3 4 5, so 1 2 3 4 5, and now then the paired one, so the 3 will be empty. So 3 are empty. For each spin it will be half, so this S will be 3 half, and for d orbital L is equals to 3, that gives us J of L plus S, which is 3 plus 3 by 2, that turns out to be 9 by 2 is equals to 4.5. Let me label this as equation number 2 and this as equation number 3. Right, now we know the J, so we can substitute 3 in equation 2, substituting equation 3 in equation 2. What we get is G is equals to 3 by 2, which is a constant, plus SS plus 1. SS plus 1 is nothing but 3 by 2 times 5 by 2 minus LL plus 1, 3 times 4 by 2 times 9 by 2 times 9 by 2 plus 1. So if we solve this equation, it will be 3 by 2 plus 15 by 4 minus 48 by 4 divided by 9 and 11 by 2. So if we solve it, it will be 15 minus 48 will be 33, minus of this will be 4 times 2 by 99 g is equals to 3 by 2 plus, so this will be minus 1 by 6. So if we do so, 3 by 2 minus 1 by 6, so we can take it to each other in para, minus 2, 16 by 12, which is roughly around 1.334. So now we know the value of the G, which is the Lambda G factor. So now the G is Lambda G factor. For cobalt is nothing but 1.334 roughly. This, let's me label this as equation number 4. Now, since we know the Lambda G factor G and we know the relation between chi molar, we can substitute these equation in equation number 1. So we can substitute equation 4 in 1. So what we get is chi molar is equals to Na times G mu B, where G is the Lambda G factor square, by 3 J plus 1 divided by KBT. So if we replace it, chi molar, N is Avogadro number 1.023 into 10 power 23 times G is 1.334 times mu B is 9.27 into 10 power minus 11 square by 3 times, so here also time is going j plus 1, so 9 by 2 times 9 by 2 plus 1 is 11 by 2, yeah, divided by 3 times kbt is 1.38 into 10 power minus 16 times 1768 is the temperature at which cobalt turns into the vapor phase. So the chi molar is roughly 3.11 into 10 power minus 3 centimeter cube per mole. Yeah, so that's how we calculate uh, the paramagnetic contribution to the Curie susceptibility. So the Lambda G factor formula, which is given as for 2D material, is G is equals to 3 by 2 plus SS plus 1 minus LL plus 1 by 2JJ plus 1, where S is the spin quantum number, L is the orbital, and J is the total quantum number, total angular quantum number. So referring the class notes, we wrote the uh, Curie susceptibility formula, and now we extracted the Lambda G factor G for cobalt. H is equals to 3 half, leading to J of 4.5. If we substitute these values, what we get the G to be 1.334, and if we substitute the value of the G, we get the chi molar paramagnetic susceptibility of the order of 3.11 into 10 power minus 3 centimeter cube per mole. So that's about the first question. If you have any doubt or question in it, you can ask in the comment section. Yeah. So if this is clear, then I will move on to the next question, which is Question number 2. If there, so the question number 2 goes like, if there are n moments non interacting with each other, then determine the free energy expression and the mean energy expression for the system. So that's the question. So question goes like, if there are n moments not interacting with each other, not interacting with each other, determine the expression for the free energy F and the mean energy E of the system. Yeah. So in these kind of the problems, what we look for is the partition function. If you know the partition function, then we can calculate the Helmholtz free energy from there easily, right? So first let's understand the system, what the system is. So system and partition function. Yeah, so we have in the given problem, we have n non-interacting moments with each moment having magnetic moment mu. So in this case, if the mu is there, if the like each magnetic moment can have the magnetic moment mu, then in that case the possible energy states will be either plus mu b or minus mu b depending on the spin orientation. So possible energy states are either E is equals to mu b or E is equals to minus mu b. These two states are possible. So if you have the energy states, then the partition function can be easily calculated from the sum. So okay, so let me just write in partition function which goes like capital Z1 equals the summation of e की power minus beta e I, where I is equals to 1 to infinity. Right, in this case I is 1 to 2 because there are two energy levels only. So if we do so, this exercise e to the power minus beta mu b plus e to the power beta mu p. So this is 2 cosine hyperbolic beta mu b. So this is the partition function with beta is equals to 1 by kbt. Kb is the Boltzmann constant and T is the temperature, right? This is for one particle, but now we have capital N non-interacting particles. In that case, your partition function goes as z1 to the power n, which is 2 cosine hyperbolic beta mu b to the power n. Now we are supposed to calculate the free energy and the mean energy, right? So the free energy is nothing but the Helmholtz free energy. So this will be step 2. Yeah. So this is step 2 in which we calculate the free energy. Free energy F. So the
இன்னைக்கு லீவ் போட்டியா நேற்று லீவு நாளைக்கு லீவு அதனால
Helmholtz
இன்னைக்கு
free energy F is nothing but minus kBT ln z. So now we can substitute our value of the z, and if we do so, what we get is F is equals to minus n kBT ln 2 cosine hyperbolic beta p. Now since we know the free energy, which is also known as the Helmholtz free energy, now we will aim to estimate the mean energy EVA. Yeah.
அங்கிருந்து ஒரு 3 கிலோமீட்டருக்கு வந்து காலேஜ் பஸ் காலேஜுக்கே பஸ் இருக்கு பஸ் ஹாஸ்பிட்டல் போயிட்டு வரதுக்கு அங்கிருந்து
I'll estimate the mean energy U star.
ஐயா
Second.
ஐயா அம்மா நல்லா இருக்கறாங்களா நல்லா இருக்கீங்க
So E goes as E star is minus d ln z by dp equals to minus d by db of ln z. Ln z is nothing but minus n kbt ln 2 cosine hyperbolic beta mu b. And if we do the exercise of this of solving this equation, what we get will be minus n 1 by 2 cosine hyperbolic beta mu b times 2 mu b sine hyperbolic beta mu b. Gives the E to be minus N mu B tan hyperbolic beta mu B. Yeah. So this is the mean energy. So mean energy we calculate to be the first derivative of the ln z with respect to the magnetic field B. So if you do so, minus kBTR cos hyperbolic beta mu B, then in that case if that is the derivative, it will be minus n by 1 by 2 cos hyperbolic beta mu B, and then it's multiplied with the beta mu B sin hyperbolic beta mu B. If we do so, we get an energy, main energy is equals to minus n mu B tan hyperbolic beta mu B. So if anyone has question or doubt on this one, they can ask in the comment section. I'll be happy to address your concerns. And if there is no question, then we will move on to the next problem. Yeah, 1 second. Let me get some water and then I'll continue. Just give me a minute. Yeah. So, and now the next question which I'll be phrasing is on the determining the form of the free energy. So the question goes like, this will be the question number 3. So if M is the magnetization, if M is the magnetization of an Ising ferromagnet, where Hamiltonian is also given, where Hamiltonian is H equals to minus J, Ij, Si, Z, Szz. If M is a magnetization of an Ising ferromagnet, where Hamiltonian H is equals to minus J times Siz and Szz. So in this case, our Hamiltonian is equals to minus J Siz Szz Ij. Now we can have a configuration where all spins are up or all spins are down. That gives us the two energy states. So H for up spins, so H will be minus j times half times half is minus j by 4. Yeah. Similarly, we can do the same exercise for the all spins down. Now we can have another state which is h4. H4 all spins down. H equals to minus j times minus half times minus half. It also gives turns to be minus j by 4. Yeah. So we have up spin, we have down spin. So since for both the spins, if we have down spin or up spin, the Hamiltonian is an invariant under change in spin. Since Hamiltonian is invariant under gas change in spin. This is Hs is equals to minus s. Yeah. So since it has to be invariant under any change in the spin, and the magnetic moment m goes as 1 by n summation over I Sij. So for change in spin also, minus m is equals to 1 by n summation over I Sij. This implies f has to be an even function of m. For example, what I mean is like if m is the magnetization of an Ising ferromagnet and where Hamilton is also given, then in that case, first we will see for the up and down spin cases. If the energy is same, it means if they are degenerate, then in that case, your magnetization m is equals to 1 by n summation of I Si square for change in spin, right? But this f remains the same. It tells us that okay, it has to be an even function of m. So our free energy, if we take to be f naught plus am square plus bm to the power 4. This is correct. The reason being it has even symmetric under symmetric under spin inversion. That's why f will be an even function. Yeah. So Having said that, now we can move on to the next question, and which is more related to the very first question which we discussed, the Landesi factor, and based on that, calculating the Curie susceptibility of this gas. So the question goes like, yeah, one second. Yeah, so someone is saying that after differentiation, should there be a KBT in the numerator? Hmm, actually, there should not be any KBT at the forefront itself, because if you see it's d ln z, and if I'm taking ln z, so in the ln z is nothing but minus n times ln 2 cos harmonic, so minus n times ln 2 cos harmonic, so there should not be any KBT. Yeah, but earlier I think I just wrote from the Helmholtz energy, but it's ln z, so the answer remains the same. This will not come, the KBT will not come in the numerator. Yeah, I think this clears it out. This is the question which I saw in the chat box. That's why I addressed this one. And having said that, I will move on to the next question, which is nickel form an atomic vapor at given temperature, let's say 2000 Kelvin. So nickel, which is the atomic number Ni Z is equals to 28, forms an atomic vapor at 2000 Kelvin, and this vapor can be considered ideal gas. So what is the, this is very similar to the very first question which I discussed in the class. So what is the paramagnetic contribution to the Curie susceptibility of this gas at 1000 Kelvin, and the answer need to be SI units. So first let's calculate the Landesi factor as we did in the very first question. So the Landesi factor goes as G is equals to 3 by 2 plus S plus 1 minus L plus 1 upon 2J, J plus 1. So this is our equation number 1. In this case, nickel, for nickel, the Z atomic number is also given. Z is equals to 28, and this tells us that the band is filled like argon 3D8 and 4S2. So in that case, if it's an argon here, you will take it to be 3D8, 1, 2, 3, 4, 5. So 3d8 1 2 3 5 4s2. Therefore, spin is equals to h is equals to half plus half equals to 1, and L is equals to 4 plus 2 minus 1 minus 2 is equals to 3. That gives us J is equals to L plus S is equals to 3 plus 1 is to 4. This is equation number 2. The earlier one was equation number 1. Since now we have all the ingredients ready, let's say J, S, L. Now we can substitute these values in equation number 1 to estimate the G. Substituting equation 2 into equation 1. If you do so, what we get, the lambda G factor to be 3 by 2 plus S plus 1. S is 1. 1 plus 1 is 2 minus 3 times 4 divided by 2 times J is 4 times 4 plus 1 equals to 3 by 2 plus 2 minus 12 by 8 times 45. 8 times 5. I'm writing 45. Yeah. So G is equals to 3 by 2 minus 10 by 12. Yeah. Mhm. 3 by 2 minus 1 by 4 is 12 minus 2 by 8 is 10 by 8. Yeah. Aye. So this gives us to 5 by 4. The Curie susceptibility we know. So this chi molar is equals to Na square Jj plus 1 divided by 3 kBt. Let's replace these values, and if you do so, what we'll get is chi molar is equals to 6.022 into 10 power 23 times 5 by 4 times 9.27 into 10 power minus 24 times 4 into 5 divided by 3 to 1.38 into 10 power minus 23. So chi molar 3.906 into 10 power minus meter square per mole. So that's how we calculate the Curie susceptibility for the material nickel and a temperature of 1000 Kelvin. So this is it. These are the, I think this was question number 3 or 4. This was question number 4. Till now, at this point, if you have any question or doubt, you can ask in the comment section. I'll just take a break for water break. Then you again. This is question number 5. No such question is there. Then I'll move on to the last time we solved in the CGS and this time in. So it will be asked in the question. So if it asks about that you provide your answer in SI units, right? So you give it in SI, or if it doesn't ask about the units, then you can provide it either CGS or SI, whichever is correct. So that's not an issue. Yeah. So now the next question is what is magnetic magnetic susceptibility? Susceptibility. Diamagnetic material. So we know the magnetization N is equals to magnetic chi times the magnetic field H. And in, if you have your diamagnetic material and you apply H in this direction, then your domain will get aligned in opposite way. Right? Your magnetization in the opposite direction. So if your H is plus Z direction, your M will be minus Z direction. Right? Then that tells you that okay, that's only possible if your chi has a negative sign. This implies chi is negative
Excuse me, sir.
for diamagnetic materials. So is this voice clear now? Or is it still breaking? Yeah, I do see a hands up from Yamansi. I can see your hands up. Can you please type your message in the chat box? Is the voice clear now? You're getting it from multiple people. I see. Don't see the reason why it should be there. Multiple people. Anyways, let me just check. An exhaust is randomly selected. What was that exhaust maybe? I don't know, but that will help or not. I'm really sorry. Currently, I'm out of the station and okay. I think someone create bar. Okay, let me just see if I can mute. Yeah, I see someone. Okay, I'll mute everyone. Yeah. mic should be on. That's what I can see, at least from the transcript material. So yeah. So is it audible now? Yeah. Thanks, Mansi. Thanks a lot. And I request everyone, please keep your mics off if you don't have anything to ask, because sometimes it, as you can see today in the class, it bothers the communication and it's not something which we would like to be having in the class. So just a quick recap over the last question. What is the magnetic susceptibility? As I was saying, if you apply a magnetic field H which is in the plus G direction, then in the diamagnetic material you will be having a magnetization which will be in the opposite minus G direction. So the relation between the magnetization and the magnetic field is related with the chi, which is the magnetic susceptibility, and for a diamagnetic material, the susceptibility is negative. So if you are given options like, for example, susceptibility based options, then it becomes easy to identify. For example, if the question asks what is the susceptibility and you are given an options A, B, C, and D, which says like 2 into 10 power 5 minus 5 centimeter cube per mole, minus 2 into 10 power minus 5 centimeter cube per mole, or maybe 3 to 3 into 10 power minus 4 centimeter cube per mole, or 0. Then in that case, for the diamagnetic material, we know the susceptibility is negative. Option B will be correct one. So this kind of question may come in your exam, and you should be prepared for these questions. Yeah. So this is about the magnetic susceptibility. Now moving on to the next question. So how to estimate the numerical number? Let's say here it was option and it could be easily identified with the sign of the susceptibility. But in some question we might be asked to evaluate the susceptibility in quantitatively, not qualitatively. So in that case, for example, I'll put forth a question which is the diamagnetic susceptibility of atomic genome, assuming r square roughly as a naught square, and the question asks to evaluate the diamagnetic susceptibility in CGS units. In CGS, that will be centimeter cube per mole, and a naught is a very well known fundamental constant kind of thing, which is the Bohr radius, 10 power minus 8 centimeter. And then we are asked to evaluate the magnetic susceptibility. So the solution lies in the class notes. As you can follow up the class notes, that the chi molar will be molar susceptibility will be minus z is the atomic number, e square by 6 mc square times Avogadro number times expectation value of r square. Z is for xenon is 54. Electronic charge is 1.6 into 10 power minus 19 coulomb. Mass is 9.1 into 10 power minus 31 kg. C is speed of light, which is 3 into 10 power 8 meter per second roughly. N is Avogadro number, 6.62 into 10 power 23 mole inverse, and R is roughly A naught is equals to 0.529 into the power minus 10 meter. If you substitute all these quantities into this equation, what will you get is chi molar is equals to roughly minus 42.66 into 10 power minus 6 centimeter cube per mole. So what you imply from this one is the numerical number is minus 42.66 and 10 power minus 6 centimeter cube per mole. Additionally, the negative sign suggests the material is non-magnetic. Material is diamagnetic actually. Yeah, material is diamagnetic. That's what it also tells. Yeah, yeah. Now the next question is based on the entropy. The question is a system of n non-interacting spins with spin value s has a total entropy equals to, we know that the total entropy, total number of states are, total number of states as omega is equals to, if there are n particles it will be power of n, and for spin s total values will be 2s plus 1, and for n non-interacting particles it will be 2s plus 1 to the power n, right? And entropy, we know that s is equals to minus kb ln omega, where omega is the total number of states, and if we do so we get minus n kb ln 2s plus 1. Yeah, yeah. So this is about it. If you have any question or doubt in these questions, please let me know. I'll be happy to address your questions or concerns. Oh, and the next other type of questions which can also come or show up will be, that will definitely I'll discuss in the next class tomorrow. I think it will be tomorrow. Yeah. So currently I'm in the US. The time is offset by 12 hours. So currently it's night around 12, around it's around 11:40 in the US. I'm here for a conference, so times are offset. I really apologize for this delay in the classes. But yeah, for this week I'll have to do that. After that it will be regular classes. So I'm really sorry for that, guys. And other than that, tomorrow maybe I'll take a few more questions, which will be determining the susceptibility, having, if a system is three level system, there you can have your energies to be of the three level, and in that case you write your partition function, and from your partition function you'll be writing your magnetization as mu spin number and your magnetic field. And if you do the exercise, you will be able to extract the magnetic susceptibility, because the relation will be magnetic field is equals to this susceptibility times magnetization equal to susceptibility times the magnetic field. And from the prefactor we compare the value and can extract the susceptibility. This is something which I'll be discussing in maybe mm, in the next class. And in today's class we discuss about the susceptibility, the diamagnetism, and uh, uh, the qualitative and the quantitative numbers of this Curie susceptibility. And depending on the given Hamiltonian for the spin degenerate bands for a up and down, we found that okay, uh, this free energy has to Helmholtz free energy has to be an even function, because the Hamiltonian is symmetric under spin inversion. And before that, the question which we dealt was estimating the mean energy and the Helmholtz free energy. And this gives us an idea like how the free energy in a system behaves as a function of the temperature, magnetic field, and this Bohr quantum number. So all those things we discussed. If you have any question or doubt on this one, please do ask in the comment section, or maybe in the tomorrow's class. I'll be happy to address that one. And if not, I think we can conclude the class here, and we can meet in the next class maybe tomorrow. I think evening for you guys and morning for me. Yeah. Thank you for being in the session in the early morning. Yeah. And uh, with this one, I'll conclude the class. So this is open to questions. That's it.